Next, let's talk about how to get the transfer functions. So there's a couple ways to do it. One way is what we call the equivalence, like a linear assumptions. So EQL, which one of the options that are available in your software package, like DeepSoil, and also like other options being available is the fully nonlinear effective stress analysis. So that one is really complicated, and it took like a lot of effort to learn and also to develop the software. So the major difference between Shake and Deep Soils is like a Deep Soils is capable to do the fully nonlinear effective stress analysis. So that's why, like the Deep Soil is more like updated like developments. So the original Shake come out from in the early 70s with from like Berkeley and directed by Professor Harry Seed. So Professor Harry Seed is the father of geotechnical earthquake engineering. So he started the whole thing back in the 60s at Berkeley, and at that time the PhD student worked for him as Schnabel. So if you get involved in some East Coast project, or like somehow like you go to East Coast work for at some point for a career, you will know about Schnabel, because Schnabel is he established a famous engineering consulting firm mainly at the East Coast called Schnabel Foundations and Schnabel Engineering. And pretty much like Schnabel started his career at Berkeley as a graduate students to make those like equivalence linear site response analysis in the early days. And it is not easy because there's a lot of repeating like calculations, solving differential equations. And back to the 70s or the late 60s, there's no like modern computer available, and in order to solve for those like iterations at Berkeley at that time, so they at Evan Hall. So Evan Hall is where like the math department's at. At the basements, they have a whole like a setup that using punch card. Simple machines to use punch cards to do the repetitive mathematics simple calculations. So it took that much like a space and time, I think, like for the punch cards to go through the whole loops to do the iterations process. It may take days, and nowadays like even with your cell phone you get the answer right away. So technologies does advance a lot. So that's the Schnabel's like a Shake program come out in the early 70s. The whole framework come out, the equivalence linear analysis come out with the early on in the 70s, and they have a major updates in 2000. So Shake 2000 is still like being, I think it will be still like sitting around for quite a few years, because the whole geotech earthquake engineering business or the industry is highly driven by people from Berkeley, and especially like if you work in California. So when I was going to grad school, like I was learning to use Shake 2000s, and I need to pay a fee for that. It's not cheap, even though it's just a equivalence linear analysis. And in the past decade, so 10 years ago, we started on the Deep Soil project at University of Illinois Urbana-Champaign, and it took them a couple PhD students. It took like a 10 years of period to come out with the Deep Soil software. And the major upgrade is able to do a fully nonlinear effective stress analysis. And it's really complicated. I don't want to, you're way beyond the scope of this course, but it does have the options of doing a equivalence linear analysis. So the major difference here is they try to capture the gradation curve, which is non-linear. So that's why in the previous lecture we try to talk about how to establish the modulus reduction curve and also the damping ratio curve. Those curves are nonlinear, and it's not easy to run nonlinear analysis. And the equivalence linear analysis is a smart way on try to like do simple analysis, kind of like cheating a little bit. They are kind of linear analysis, but they take advantage of the iterations to capture the fully nonlinear aspect. So for the totally nonlinear effective stress analysis, is much more complicated. I don't think we can spend time to talk about that in this class. But imagine if you do a PhD nowadays in geotechnical engineering, pretty much you need to work on the nonlinear effective stress analysis for dissertations. But anyways, the coding part for nonlinear analysis, equivalence linear analysis, plus solving the differential equations that we saw before with the using the Kelvin Voigt model to describe the shear stress of soils is not too bad. And I think at master level, we can code that in MATLAB. Part of my graduate work, I have done that too. I have simple problems in the lab, simple soil profiles, not too many soil layers, and the other day is just solving differential equations with iterations. So what is 1D equivalence linear analysis? Yes, again, they try to find the transfer functions. Again, we have seen this. The transfer function is the key, and how to find or to modify the transfer functions is based on the nonlinear gradation curve that we established in the lab, and also from the field with the field data and also the lab data, so we can have a site-specific gradation reduction curve. Or if you don't have the luxury to do the lab test like a semester project, so typical soils, the researcher has established that. So for typical sand or clay, and how the curve look like, or based on the PI, the plasticity index, or based on the sand relative density, then you have different shape of the curve. So starting from those curves, how to find the transfer functions? Yes, first you will select your initial point. Start from the G1 and D1, which is the G max and D mean. So when shear strength equals 0, you find your G max. You assume the shear modulus is at its maximum values. So this is your G1, and this is your D1. So it makes sense. So just before earthquake happens, right? There's no displacements, so that's why the modulus is at the greatest values. And then the G, and then you know the D. You can substitute it to the those differential equations, and then you can find the transfer functions through this differential equations, because now you know the G, and then the D. So which is D is part of the viscosity coefficients, and then you can solve with these equations. You can find the transfer functions, and also solve for the gamma, the shear strength. And shear strength is related to the displacements. So you can solve for the the G, and then you can solve for your gamma 1. So this is your gamma 1, and then you compare your gamma 1 to the curve that you have. So you go back to the gradation curve. Now you have your corresponding G2, and you compare your G2 and G1. So same thing with the D, but compare G1 and G2. If G1 and G2 is about the same, that means you will find the answer. You find the correct shear strength and transfer functions. Then you can use the transfer functions to move on to the next layer. But if this is different, then you will iterate. You will repeat the process. Then you use G2, and then go back to your to find your corresponding shear strength again. So this could be your updated gamma, and then you compare your updated gamma with your gradation curve, and then you find the next G3, and then now we check is your G3 close enough with your G2. If yes, then you stop. Within the threshold, then you can stop. Then you call it is you find the transfer function already. So this will kind of like a iterate process to until the point that the G and the D, the next step is this close to the current step is this close to the previous step. So that's the way that we find the transfer functions with the equivalence linear analysis approach. And there are some assumptions has been laid out in order to use this method. First, like the horizontal layer systems will kind of like infinitely extend in the horizontal directions. So you purely like a 1D method, and each layers you will have its own like a soil properties, both the G, the damping, and also the unit weight and the thickness. And we also like assume the shear stress is continuous throughout the layers in horizontal directions, and we only work for shear wave, and there's no P wave. This is not true, because when earthquake happens, this is kind of like a body wave. We have both P wave and S wave, but most of the damage is done by the S wave instead of the P wave. So it's not like truly accurate, but this is okay for engineering applications. And actually, this is a linear method. This is a linear method. You only adjust the elastic soil behavior, but the iterative approach try to capture the nonlinearity of the modulus reduction curve and also the damping ratios. So kind of like cheating a little bit. So that's why we call it equivalence linear.